Good morning. We're going to continue today's discussion of solutions by talking about different ways we can report the concentration of materials that have been dissolved in solution. And then we're going to continue talking about solutions, and we're actually going to talk about some of the other properties of materials that are in solution. So those are some, different solubility effects. Some things will make things go faster, some things will make things go slower. But in regards to that, but oftentimes we want to actually report what the concentrations are. And there's a couple of different ways we could do that, depending on what you're looking at. You can report this as weight percent, you could record it as a percent, or you could record it in terms of moles. So kind of four commonly used methods of reporting concentrations, one of which is this idea of weight percent, where you basically take the weight of the material that you've dissolved, so the weight of all the solutes, and then the weight of the total solution, which would be the weight of the solute and the solvent together, and basically how much of this solution is the thing I dissolved in it. Sometimes, and that's good particularly for solid materials that you're trying to dissolve. So if you have a solid material, you want to dissolve it, you weigh it out, and then you weigh the total solution of the whole system. You can also do this for volume. If you have two liquids, how much of this liquid is here, how much of the other liquid's there, dissolve them both together, figure out the total volume. And sometimes they'll use this intermediate combination, which has both weight and volume together. So if you have a solid dissolved in a liquid, sometimes they'll use that. But that's the least commonly used of all of these different methods. Frequently, it's done in weight or weight-volume percents. But other times scientists want to know how many moles there are. So they don't care necessarily how many grams there are. They don't care what the ratios are. They want to know how many moles of this particular chemical is present in the solution. And that's where they use things like molarity, which is the number of moles of the solute, the thing you're dissolving, and the total number of liters of the solution. So it's moles per liter. And if you're working with chemicals and trying to figure out how much different materials are present, that one can be a pretty useful one as well. So it kind of depends on what applications you're doing. Certain ones of these are more useful at times than others, but you'll kind of see them all be used in some way or another. Especially around your house, you'll see a lot of weight percent sample concentrations. So for doing when you're doing the percents, one of the key things is that we're always dealing with the amount of the solute, that's the part, divided by the amount of the solvent, the solution. And the solution is both the solute and the solvent. It's not just the solvent alone, it's also the mass of the solvent and the solute together, because it's a total mass. It's not just the mass of one part of it. And the same thing for the solution volume. It's the total volume of the entire solution, not just the solvent and not just the solute, but both of them together. So whenever we're doing these types of calculations, we want to make sure we're using both the solution volume or the solution mass, the entire system solution, not just the solvent and the solution solute separately. You have to add them together for that part. So when you do those weight percents or those volume percents or those weight volume percents, you always have to remember that the first thing you have to do is figure out how much, what they're asking for, and then how much of the total solution you have, as well as what amounts of solute that you have. Because when you do these calculations, it's the solute, either weight or volume, divided by the solvent weight or volume. So in this case, we're looking at an example of a weight percent, so W/W is what they're asking for. And this particular solution has two components. It has 15 grams of sugar, and that's going to be our solute. And it also has 100 milliliters of water. Because they gave us the water mass gave us water volume, but we need water mass, we're all going to have to convert volume into mass by using the density. So that's another thing we're going to need to work on with this particular example here. Now what we're doing is, because we're doing weight percent of the solute, solute in this case is the sugar, so the mass of the sugar up here on top is going to be divided by the mass of the total solution, which is going to be both the mass of the water and the mass of the sugar added together. So it's not just the mass of the water, it's the mass of both components. So what we're going to do for that is we're going to take first and figure out how much the mass of the water is. We know we have 100 milliliters of water, but we also know that water has a density of 1 gram per milliliter. So if we were to multiply the density times the volume, then we would get the concentration of the water in volume. We would cancel out constant volume here. We'd be left with grams, and that's what we're looking for, grams of water. So we have 100 milliliters of water, multiply that by the density of 1 gram per milliliter, turns out we have 100 grams of water. Now when you look at water, you also have this solution that has 15 grams of sugar, 100 grams of water. So the total concentration mass, the total solvent mass is 100. The total solution mass, which is the mass of the solute plus the solvent, is the 100 grams of solute plus 100 grams of solvent, which means our total mass for this system is 115 grams. And that's the value that we're going to use down here for the mass of solution. We need the mass of the solution, which is the mass of both the water and the things dissolved in it, in this case the sugar and the water together. So now we have everything we need. We have the mass of the solute, the 15 grams of sugar. We have the mass of the total solution, 115 grams, and we're going to divide one by the other to get the weight percent. What percentage of the weight of this solution is the solute? So we put that in. What percent of the weight of this solution is sugar compared to the total volume? And it's 15 grams divided by 115 grams, which comes out to about 13% in this case. So 13% of the weight of this solution comes from the solute, which is the sugar. The other 87% of the solution's volume comes from the mass of the water, which makes up the solvent. So that's an example of a weight percent calculation that you could do to report the concentration of a molecule in solution. So this is just one example of doing that, and this is an experiment you can do at home if you want. If you want to try and make rock candy or candy sugar, what you do is you just dissolve sugar. So sugar is extremely soluble in water. Sugar dissolves very, very well in water, and it actually is very temperature dependent though. So if you look at different samples of water at different temperatures, the hotter the water gets, the more it goes into solution, and you can go really, really warm and you can saturate a sample. And it turns out at 60 degrees Celsius, which is not boiling, but it's still pretty warm of water, you can dissolve 150 grams of sugar in 50 grams of water. So you can basically put 3 times as much weight of sugar as there is water weight. So you can have a really, really saturated solution, lots and lots of sugar in the water. But then as the water cools down, the water isn't able to dissolve as much sugar anymore, and some of the sugar has to leave the solution. Because when you go down to lower temperatures, it goes from having 3 times as much sugar in the water to only at room temperature about twice as much sugar in the water. And all that extra sugar is going to leave the solution, and it'll form crystals as it comes out of solution, because it'll fall out of solution rather slowly. And if you put a little stick in the water, the solution will actually start to crystallize onto that stick, and you'll form a sample of rock candy. And you can add different dyes and flavorings, and you can make these if you want. You can also just put a string in the water, have it hang down, and watch those crystals grow. And if you ever had a crystal growing kit or anything when you were growing up, they're doing the same thing. They're just using different chemicals. This is using a solution of sugar and water. Some of the solution crystal growing kits use either sodium sulfate or copper sulfate for a nice blue solution with pretty blue crystals. Depends what you're trying to do. But you can also do this with sugar at home if you're looking for something to do. And the nice thing about this experiment with the sugar is you can eat it at the end. It's just sugar. Or you can dissolve it in your tea or your coffee pretty quickly. So for this solution here, we're going to try to figure out, right, we've got 2 different concentrations, just trying to calculate the percent weight per weight of these 2 solutions. So weight is the solute mass, in this case the mass of the sugar, divided by the solution mass. So we've got one sample right here. The entire mass of this sample is 50 grams of water and 150 grams of sugar. So that total sample would weigh 200 grams. So if you were to start with this experiment and you were to add 50 grams of water and then you were to keep pouring the sugar in until it doesn't dissolve anymore, you would watch the mass go from 50 all the way up to 200. The solution weighs 200 grams, but 150 grams of that 200 grams is sugar. So it turns out 150 of the 200 grams of sugar, 75% of the weight of that solution at 60 degrees is sugar. So that's a 75% weight per weight, or W/W, solution of sugar in water. You could do the same thing for the other solution, the colder temperature solution, except now we only have 50 grams and 25 grams. So we have a total solution volume of 75 grams now instead of 200 grams, so there's a little bit less weight. And of that 75 grams, though, 50 grams is the sugar. So it turns out we now have 50 grams of sugar dissolved in 75 grams of solution, and we have about a 67% weight per weight, or W/W solution. So as the solution cools down from 60 degrees to 24 degrees, it goes from 75% sugar down to 67% sugar. And that extra 8% of the solution, that was the sugar 8%, falls out of solution and forms these little rock candy samples. So that's one way you can do this experiment at home, and it's just showing different ways of recording masses of, or percents of concentrations of a sugar solution. We're using percent of the total mass, or the total weight in these cases. So anytime you see a W/W percent, they're talking about the percent of the total weight that is the material that you're studying. So in this case, 75% of the total weight of a sugar water solution is sugar, and then as it cools down, only 67% of the total weight of the sugar water solution is sugar. So that's one type of calculation we can do, the W/W calculation. Another way of reporting concentrations of solutions, this one doesn't come up as frequently as the weight percent or the volume percent, the WW or the VV, but another one that does come up every once in a while is a weight volume percent. This is the percent of weight divided by the volume, and it's a little interesting, not quite the same as the other two, but every once in a while you'll see this. And basically this is a report of how many grams per milliliter you have. So if you have a solid sample that you're dissolving in a liquid solution, a liquid solvent to make a liquid solution, sometimes you may be reporting the mass per milliliter. And that's what this example is showing here, another way of reporting that concentration. So for this type of situation, you're reporting how many grams of solute are present in the total volume of the solution. So in our case here, we have 8.95 grams of the solute, which is the mass of the solute, 8.95 grams. And we also have a volume of solution, a total volume of 50 milliliters of solution. So now we have our solution volume, 50 milliliters, our solute mass, 8.95 grams, and we put those into this equation to get the final percent. So in this case, we would divide 8.95 grams by milliliters, 50 milliliters. This is grams per milliliter. Other ones were grams per gram, or liters per liter, or milliliters per liter. This is grams per milliliter. It's a special unit that we use. And when you do that, you get 17.9. Now, grams and milliliters aren't the same unit, but for this case, you actually can let them cancel each other out, even though grams is a unit of mass and milliliters is a unit of volume, but it's okay for this case to let those cancel out and ignore those units so that you have a mass of 17.9%. So 17.9% weight volume is the concentration for this particular solution here. And then the final type of way of reporting concentrations by percent is by volume. What percent of the volume is made of solute, and what percent of the volume is made of solution total? That would be both the solution, the volume of the solvent, and the volume of the solute to make up the total solution volume. And this is more frequently used when you have two liquids that are being mixed together. So if you took a glass of water and a glass of some other liquid, and you want to mix those together, two liquids mixing together, rather than using mass for both, you could just use the volume. You know, you took 20 mils of one thing, 15 mils of another, mixed them together, you have a total volume of 40, 20 out of 40 is 50%. So you have a sample there. Now, for this particular example we're using here, again, volume percent, you might notice, though, one of these units is in milliliters, the solvent is in milliliters, and the solvent is in liters. So because we're dividing one by the other and adding them together, we have to make sure that our units are the same for both. So we can either use both in milliliters or both in liters, but we can't do one in milliliters and the other in a liter because otherwise that way our units won't cancel. We have to be both in the same type of unit for this calculation to work. So the first step we're going to have to do is convert one of those to the other unit so that when we do our second step of taking the volume of the solute, right here, the 250 glycerol, and the total solution volume, which is going to be the glycerol plus the water, then we're both in the same unit. Those units cancel and we get percent. So we're going to convert glycerol from milliliters to liters. We know that 1 liter contains 1,000 milliliters. So our milliliter here and our milliliter down here cancel out with each other, and we're only left with units of liters. So we've turned 250 milliliters of glycerol into 0.250 liters of glycerol. It's the same volume, just reported with a different unit. So now we have both glycerol and water on the same scale. They're both on the liter scale, which means we can add them together and figure out what the total volume of the solution is, because we have to divide that 0.25 liters of glycerol by the total volume of the solution. And the total volume of the solution is the volume of the glycerol and the volume of the water added together. So we add those together. The solution volume, 0.250 liters of glycerol plus 1.25 liters of water. We have a 1.5 liter volume total for this solution. So this solution, if you were to look at it, would have a total volume of 1.50 liters. That makes sense. 250 milliliters plus 1,250 milliliters, or 0.25 liters plus 1.5 liters, add up to 1.5 total liters of volume. So we take our total solution volume, 1.50 liters, put that down here on the bottom, and then we take our solution solute volume, which in this case the solute was 250 milliliters or 0.250 liters. So we put that number over here. So we have our amount of solute divided by our solute plus our solvent, which gives a total volume of the total volume of the solution. So we divide 0.250 liters by 1.5 liters of solution. We get liters canceling, liters on top cancels with liters on the bottom, and we get 16.7%. 16.7% of the volume of this solution is glycerol. The other percent is made of water. So 16.7% of the total volume of the solution is the solute in this case. Another type of solution that we could do, though, is the V/V, or volume/volume, and that one's pretty commonly seen as well. And if you just go into the medicine cabinet, you'll see witch hazel bottles, you'll see isopropyl alcohol, the rubbing alcohol, you'll see peroxide. They're all reported as percent, usually percent V/V. So two different kinds of alcohol, rubbing alcohols you can get, the 70% and the 90%. And actually, a recent study was showing that actually the 70% may be slightly more effective at killing bacteria as an antiseptic than the 90%, because that extra little bit of water allows the bacteria actually to get into the cell and kill it, but doesn't hurt, because if you have 90% at home, you can always add some water and water it down to 70% if you wanted to. So this is trying to figure out what's the difference of the amount of water that's in both of these samples. So we have a 200 milliliter sample of 70% volume by volume. So that means 70% of the total volume is alcohol, or 90% of the total volume is alcohol. But in both cases, we're going to have the same 200 milliliters of samples. So they just want to see, if you had 200 mils of both, how much water is in sample A and how much water is in sample B. So we know the percent volume is just the amount of solute, in this case the amount of isopropyl alcohol, in the total volume. And our total volume now is 200 milliliters. So we have a 200 volume sample in both. We also have the percent sign over on the side over here. So we have this number already, and we have the volume solution already. So we can just solve for solute volume, which is what it was asking as well. So we know this is figuring out the amount of alcohol that's in both. So how much alcohol is in the first sample? 70% of the sample is alcohol. So 0.7 times the 200 mil, that means that 140 milliliters of the 200 is alcohol. Let's see if I can just draw 200. So 140 milliliters of the 200 milliliters total is alcohol in the first sample. And then the second sample, we could do that same thing, where it's 90% and 180 milliliters of the 200 is alcohol over there. So in the first sample, we essentially have 60 milliliters of water and 140 milliliters of alcohol. And then in the sample on the 90% side, we have 20 milliliters of water in 180 milliliters of alcohol to give us a total volume. So for these two samples here, one sample had 60 milliliters of water plus 140 milliliters of alcohol. That gives us a total volume of 200 milliliters. And since 140 milliliters of the 200 milliliters was alcohol, that means 70% of the volume of the sample is alcohol. Versus for the 90% sample, we took 20 milliliters of water and we added it to 180 milliliters of alcohol. And that means that there was a total volume of 200. 180 plus 20 is 200 milliliters total. But of those 200 milliliters total, 180 milliliters was the alcohol, the other 20 milliliters was the water. So 90% of the volume of that solution was alcohol. So if you had those two samples, you can see how there's a little bit more water in the 70% sample. There's about 40 milliliters more water, and that little bit extra water is enough to make a difference in how well that alcohol kills the bacteria sometimes. So those are another example, this time using the volume percent of the solution mass, or volume percent of the solution to figure out the amount of material that's present. And you can actually convert these if you really wanted to. So what's also is kind of interesting is if you were given something in V over V, and you actually wanted to go from V over V to weight over weight. So if you want to go from volume percent to weight percent, V/V to W/W, you can do that as long as you know the densities. And that's kind of an interesting thing to see, that if you were to report the 70% isopropyl alcohol solution as V/V, but if you worked for a different company, maybe that reported it as W/W, you would each report a different number, even though you are reporting the same thing, because you're both taking the amount of isopropanol, the amount of water, you're figuring out the total volume, and then you're converting it into one common unit that you could report as. It's just two different forms of the same number, two different percents. And this only really makes a difference because isopropyl has such a low density. The density of isopropyl alcohol is 0.786 grams per milliliter, whereas water has a density of 1 gram per milliliter. So there's going to be a little bit of difference in the mass compared to the volumes. And we can kind of actually do that calculation here. Right, normally a V/V calculation just tells you how many milliliters of solute you have divided by the total concentration. And so if we had a 100 milliliter solution, a 70% V/V solution means that we have 70 mils of isopropyl alcohol and 30 mils of water. So that's just like we did on the previous page, that if we had a solution that has 70 mils of isopropanol and we added that 70 mils to 30 mils of water, we'd have a total concentration of 100 milliliters of solution. 70 mils of that 100 total is isopropanol. That gives us a 70% solution, and that would be the V/V. But if we wanted to figure out and the total solution volume is going to be 100. But if we wanted to figure out what's the mass of all these different materials, we could figure out what is the mass of 70 mils of isopropanol. And to do that, we would multiply 70 mils of isopropanol times this density value over here, and that would give us the amount of grams of isopropanol. We could do the same thing for water as well. So we do that. We figure out what is the mass of 70 mils of isopropanol. Well, 70 mils of isopropanol times 0.786 grams per milliliter. And then that means that the milliliters here and the milliliters down here cancel. So we're left with grams. So we've turned milliliters, 70 milliliters of isopropanol only weighs 55 grams. So 70 milliliters of isopropyl alcohol weighs 55 grams. We can do the same thing for water. Water has a density of 1 gram per milliliter, so 30 grams of water weighs 30 milliliters. So 30 milliliters of water has a mass of 30 grams. And the total mass of our solution is 55 grams plus 30 grams. So our solution has a total mass of 85 grams. And of those 85 grams, 55 grams come from the isopropanol, the other 30 grams come from the water. So if we were to figure out what the weight percent of isopropanol is in this solution, the weight percent is 55 grams divided by 85 grams, comes out to about 65%. So a 70% volume solution, so a solution that says 70% of the volume is isopropyl alcohol. If you were to instead report that same concentration of the same solution, but to report it using weights, you would say it only has a 65% solution of alcohol, because rather than using the volume, which says 70 mils out of the 100 mils is the alcohol, use the weights, which say that 55 out of 85 grams, you report the same concentrated solution as a different number. So it's really important if you're reporting these concentrations, if you do V/V or W/W, you have to tell them which version you're using, because otherwise you may report the wrong one. 65% weight per weight and 70% volume per volume for isopropyl are actually the same concentration, even though the numbers are different because one is calculated for weight and one is calculated for volume because of the density differences. But it's actually the same solution. We're talking about the same solution in both cases there. So it's really important that we use the right units. Otherwise, you might confuse people for that. So ppm, ppb, percent, those are all very useful for reporting a concentration in relation to the other materials that are in solution. But sometimes scientists want to know how much atoms there are, how many molecules there are, and they want to do that, and they use, instead of using concentrations and percents, they'll use moles, because maybe they're doing a reaction and that reaction needs 6 moles of a particular material. Well, how much solution do I have to get to 6 moles? Or if I need 0.1 moles of this reaction here, how many milliliters of solution do I have to get that 1 mole or that 0.1 mole? So they'll report things in concentration in mole units instead. So they'll report moles per liter. So that's molarity, and sometimes it's called capital M, so moles per liter. Capital M is 1 molar, or a solution with a molarity of 1. So you take the number of moles you have, number of liters you had. So even for a simple thing like this, if we had 1.5 moles of NaCl, so we could always figure out how many moles there are using our periodic table and just kind of looking up the formula weights of the molecules. And getting that. But we had 1.5 moles of NaCl. We have a total volume of 3 liters, gives us a concentration of about half a mole per liter. So if I needed half of a mole of NaCl for a reaction, I would have to add 1 liter of this solution. And if I needed 4 moles of NaCl for a reaction, I would need 8 liters of this solution. So if I had a recipe where I acquired 4 moles of NaCl, and some other materials, I dump in 8 liters of 0.5 molar NaCl. That gives me 4 moles of NaCl, and then I could add my other reagents to that as well. So this is a way of adding material in solution and figuring out how many moles you have so that you can handle things like limiting reagents, or you can use those stoichiometry type problems to figure out how many moles of compound you will get as a product, or how many moles you would get of different reactants that you would need. And this is just a couple other examples, right? If you're doing moles per liter, you always want to make sure that you have moles, but you also want to make sure that you have liters. So if they give you something in milliliters, we might have to convert milliliters to moles or to liters. So in this case, right, 250 milliliters, we know that every liter has 1,000 milliliters in it. And that way the milliliters up here cancel out with the milliliters down here, and those cancel in such a way that only the liters is left. So it turns out we have 0.134 moles divided by 0.250 liters. So in this case, the concentration is 0.536 moles per liter for this sample. And we could also do this for other samples too, right? So we could figure out, for our isopropyl solution, we figured out our isopropyl solution is 70% volume per volume. We also know that it's 65% weight per weight. But we could also figure out what's its concentration in molarity. So we know isopropyl alcohol has about 55 grams of alcohol in 100 mils of solution based on our previous calculation. So we can turn grams into moles. So one step will be to turn grams of alcohol into moles of alcohol using this formula weight. The other thing we're going to have to do is we're going to have to turn this 100 milliliters into liters. That's easy enough to divide by 1,000 to do. But the first thing we got to do is if we want to turn grams of alcohol into moles of alcohol, we got to figure out what the mass of the alcohol is. So we'd go to our periodic table and we would see, all right, carbon weighs 12, oxygen weighs 16, hydrogen weighs 1, and there were 3 carbons, so each carbon weighed 12. That means we have a mass of 36 on the carbons, 8 hydrogens that each weigh 1, and then an oxygen that weighs 16. So 1 mole of isopropyl alcohol weighs 60 grams. So we have 55 grams. We have a little bit less than 1 mole of isopropyl here. So 155 grams of CH308 divided by 60 grams. My grams of CH308 cancel with my grams of CH308, and I'm left with moles of CH308, or moles of isopropyl alcohol. And like we said, we have a little bit less than 1 mole. Turns out we have 0.92 moles of CH308 that is divided by 100 milliliters, or 0.1 liters. So we can turn milliliters into liters, milliliters, 1,000 milliliters in a liter. The milliliters on top cancel with the milliliters on bottom. 100 divided by 1,000. So now we have liters and we have moles. So we can figure out how many moles per liter by dividing the number of moles by the number of liters. And it turns out that 0.92 moles in 0.1 liters means that we have a 9.2 mole per liter solution of rubbing alcohol. So the 70% isopropyl alcohol that you have in your medicine cabinet, you could report that 3 different ways. You could report it as 70% volume, you could report it as 65% weight, or you could report it as 9.2 molar. And all of those would be perfectly valid ways to describe that same solution. Those are 3 different ways of describing the same solution. It's not different in any way, it's just different ways of reporting the same number. So reporting concentrations is really important, because if you say it's 70%, well, is it 70% volume per volume, or is it 70% weight per volume? There's a difference. If you say it's 70, is it 70%, or is it 70 molar? Because that's also different. So it's really important that we use concentrations with the units on them so that they know what we have, because the same solution can be reported 3 different ways with 3 different numbers. And if you don't have the right units on them, it would be really hard to tell which one is which for that. Moles are also useful if you need to figure out how many moles are in a solution. So if you have the concentration of a solution and you want to know how many moles are in that solution, you can figure that out too, because moles divided by volume gives you molarity. So if you have molarity and you have volume, you could figure out moles. So you can kind of rearrange, liters times molarity gives you moles of solute. So that's useful for figuring out the concentrations of a sample here. So in this case, right, we have 0.015 liters. We know the concentration, and it turns out that that 15 milliliters of sample that maybe you just spilt on the floor, maybe you spilt this sample and you want to know how many moles did you just spill, or you've been exposed to it, maybe you drank it or you got it on your skin, and you want to know how much MgCl2 were you just exposed to. Well, you know how much there was, you know how concentrated it was, and using the concentration and the volume, you can actually figure out that you were exposed, in this case, to 0.012 moles of that particular compound. So if you ever need to figure out what moles are present, as long as you know the concentration, as long as you know the volume, then you could do that. Or maybe you had to mix these two together, and now you need to know how much of the reagent you have present. There's 0.012 moles of that particular chemical present in that solution for the reaction to start. So concentration is pretty useful, and you can do all sorts of neat stuff with concentration. You can figure out how many moles you have. You can figure out what percent things are. But you can also go from a high concentration to a low concentration. So if you wanted to dilute something and you had a really concentrated solution, you could actually go from a high concentration down to a low concentration by kind of adding the right amount of solvent and solute. You can also make solutions of any concentration you want by kind of planning things out. But diluting is really neat and really kind of interesting thing you can do, because for any solution, the concentration of the first solution and its volume is going to be equal to the concentration times the volume of the second set of conditions. So if you had a solution that was really, really concentrated and a very small volume, and you increase the volume, you can bring the concentration down if you have a concentration that's too concentrated. So if you make a punch for a drink and you go and sip on it and it's just too much sugar there, well, what you can do is you can dilute it by adding more water, and you make the volume go up. And as you make the volume go up, the concentration goes down and it becomes less sugary flavored. And you can do that with concentration units. You can do it with the percents. You could also do it with the molarities. So any solution that you have that's concentrated and you want to change the concentration, you can use this formula to figure out how much liquid do you have to add to change the concentration to the new amount that you want to use for that. So to kind of show an example, right, we have this solution here that's pretty concentrated. You can't see the level very well, but the level's around here right now. So we have this solution, and it's 5 moles, and you can count. We'll just say each one of these spheres is a mole of solution. So we got 5 moles of solvent divided in 1 liter of a solvent. So we have a 5 molar solution that has a volume of 1 liter. But if we were to add more water or more solvent to this solution, those 5 moles would still be there. But now the 5 moles are in a much lower concentrated solution, because the 5 moles now are in a volume of 4 liters. Those same 5 moles now occupy a volume of 4 liters. So we go from 5 moles per liter over here with a 5 molar solution to a 5 moles in 4 liter solution, which means that our new concentration is only 0.125 molar. And you could also look at this by doing the calculation. 5 moles was the initial concentration, 1 liter was the original volume, so 5 here, and then 1 over here. And then on the other side, our new concentration, new volume is 4 liters. So our new volume is 4 liters, so 5 times 1 divided by 4, and that gives us a final concentration of 1.25 moles per liter. And that matches the concentration that we matched by following the moles themselves. So if you wanted to see, if you wanted to go from 5 moles per liter down to 1.25 moles per liter, how much water would you have to add to that solution to dilute it to get the solution that you want, to go from that highly concentrated 5 moles per liter down to this lower concentrated 1.25 moles per liter. And we can figure that out by using this C1V1, C2V2 type equation. You can do it again here with another example, and it works actually for concentration in terms of moles. It also works for the percent. So as long as you leave those units the same, you can go from percent to percent, you can go from moles to moles, whatever you want to go from one to the other, as long as you have a volume, as long as you have a concentration unit, either in moles or in percent, you can do it. You can use liters, you can use milliliters, you can use gallons, as long as you leave the unit the same throughout too. So we could use liters or milliliters as long as we don't change the milliliters. So if we're going to start with milliliters, we have to end with milliliters. If we're going to start with moles, we have to end with moles. If we want to start with percents, then we got to end with percents. So if we start with a percent over here, we're going to end with a percent on this side here. So our 84% solution, or our 8 molar solution, if we raise the volume from 100 milliliters to 400 milliliters, our concentration goes down as our volume goes up. So it goes from a volume of 100 to a volume of 400, We started with milliliters, we ended with milliliters. We started with moles, we ended with moles. But we went from an 8 molar solution that was concentrated in 100 milliliters to a 2 mole solution that was concentrated, that's been diluted into 400 milliliters. Or for the one down here, we went from an 84% solution in 100 milliliters to a 21% solution in 400 milliliters. So if you want to dilute something, you can figure out the concentrations by kind of doing this kind of ratio calculation for those. So it's really useful to be able to dissolve stuff and then dilute it to a lower concentration versus making a really a really large solution with a small amount. You can make a very concentrated solution and then add that to a larger amount. And if you ever handle a pool, or if you work at a pool or anywhere where they work with really large solutions, this is what they do. They make really concentrated solutions and then they add it to the big vat and let it mix out evenly rather than having to add lots and lots and lots of material to that. And especially for industrial processes where they're working with really large scale or water purification, they add just concentrated amounts of the chlorine rather than adding lots and lots of gallons of dilute chlorine to water. They add a couple larger volumes of a very concentrated solution instead. So we can use concentrated solutions to make a very low dilute solution that's kind of spread throughout by taking advantage of these calculations. So this is just one example, right? We want to take a solution that's 1.5 molar, and that's our stock or our base solution, and we want to go from 1.5 moles to a new concentration of 0.5 moles. So we're starting at 1.5 over here, and we're going over to 0.5, so that's our change in molarity. We're going to go down by about a factor of 3. And we also know on this side that we need 250 milliliters, and as long as we leave the other side in milliliters as well, that's okay. So we need some number of milliliters over here, so this times this is equal to this times this. So 250 times 0.5 divided by 1.5 would tell us the amount of milliliters of the concentrated solution that we would need to make this sample here. So we can kind of write that out. We know that we had 1.5 molar HCl solution, and we had a certain volume of that HCl solution. And because this is in milliliters over here, this volume is also going to be in milliliters over here. We know that we need to go from 1.5 molar down to 0.5 molar. And when we do that 0.5 molar, we only want to have 250 milliliters of it. So if we kind of solve that out, this shows that if you took 83 milliliters of a 1.5 molar HCl solution and then diluted it in water until the final volume became 250, then you would go from 1.5 moles per liter down to 0.5 moles per liter.